All right, how's it going, party people? So today's video is on loop unrolling and SIMD layered together. I'm not going to go over the technical details for SIMD and loop unrolling. I'm just going to assume that you kind of already know how to do those sort of things. And the purpose you're watching this video is basically to apply those concepts to optimize a linear algebra subroutine called floating point multiply and addition. So I'm going to refer to this explanation of my FMA. So it's a well-known linear algebra subroutine where you have one array that is being multiplied by a second array and being added to a third array. No scalars at all. That's why we call it FMA. Here I have a slightly different notation than most other sources, where actually that first source array is also the destination. All right. Okay, so I suppose let's go ahead and code this thing up. I'm going to code it using separate source files and then go from there. All right, so let me explain what I'm doing here. We include standard library. The purpose is to use the malloc function so that we can declare arrays of a certain size. This particular function is a benchmark function for the myFMA function, which we'll create later. We will want to create arrays that are large, that are so large you actually can't create them on the stack, which is why we have to use malloc. So if you're not familiar with C, you have to use a function called malloc, where the operating system will find a large enough space on the heap and return it as a pointer to you. And then you also have to free it when you're using this sort of paradigm. All right. So we have our integer main function. I'm not using variable arguments here, so that's why it's an empty pair of parentheses. Moving on, here is our size of array. This is an absurdly sized array. Feel free to calculate exactly the number of bytes this sort of thing would take. So this is like 20 million floats, basically. Here you'll see three uses of malloc. So when you call malloc, you have to pass the number of bytes that you want to allocate, not the number of elements, basically. So here we're using the definition of float, which, you know, it's 32 bits in most environments, but you're going to want to just use whatever the definition is times n, because this is a linear or one-dimensional operation. Malloc will return the pointer, but you have to typecast it as the sort of pointer that you want to use, and that is being assigned. This whole thing is being assigned to a floating point pointer. So this is an array of floats, and then we will call the function, which we will, as of yet, create. And then remember that when you use malloc, to always deallocate it at the end. Otherwise, you know, you may have improper garbage handling. You don't want that to happen, that sort of thing. Let's go ahead and quit this thing out. So a bit of an explanation here. We're going to use GCC as our compiler. We're going to want to display all warnings. We're going to want GCC to not optimize anything, because if it did, it would realize that we were performing linear algebra on an array filled with zeros that had nothing in it, and it would actually refuse to compile your stuff, and you would get an improper assessment on your benchmark. We want to just compile this into an unlinked binary, so -c, and I want the output to be main.o, and we're compiling off of main.c. All right, cool, no errors. So where do we go from here? I guess that leaves us with implementing the myFMA code. Let's go ahead and bring up a template for that. So what I'm going to do here is to just compile it using C first, or just write it in C, and then that'll give us our baseline estimate. So let me go ahead and fill this function out. All right, so what you're looking at here is just a C code. That is the definition of myFMA. So the first argument is the length, then 3 floating point arrays. We have a for loop that starts at 0 and iterates for the length of the array, incrementing the counter by 1 every time. And then the actual math, A of I times B of I plus C of I being stored back into A of I. And then that is it. All right. Let's go ahead and compile this thing and just get a baseline measurement of how fast this algorithm is. So as with the previous one, we're going to display all warnings. Don't optimize it, and I want the output to be myfma.o, and we'll compile this thing off of myfma.c. We'll use GCC to link both of these items, wall O0. Don't put the -c flag here. The -c flag is only for compiling unlinked binaries, and we're going to want to link it this time. We're going to call this version1.out, and I want to link myfma.o and main.o together. All right, so the output for this function, by the way, because this is just a benchmark, the output is actually you measuring the amount of time it takes to run this thing. So let's go ahead and run it. So that is 0.189 seconds. That seems pretty fast, but I think we can get that number down. All right. So where do we go from here? I guess we will apply the concept of single instruction multi-data stream to our code. Please reference the other videos about that. The idea of SIMD is that there's actually there is an underlying single cycle instruction that is capable of both dereferencing and referencing memory in a chunk of memory operations as well, to place those memory operations in a vector register that can be handled in parallel. So rather than just load one instance, there's an instruction that could load 4 parts of the array at once, and then an arithmetic instruction that will then perform independently arithmetic on each one of those elements, and then a final instruction that will store all of those elements back into the array. All right, so let's go ahead and take a look at that. So how do we start this? Well, I think a good idea is to actually get GCC to do a lot of the work for us. Please note here that when I'm doing this, you're going to want a big S flag to generate assembly code. We'll have the output be myfma.s, and I want that generated off of myfma.c. Big warning here, please do not run this instruction more than once, because if you modify myfma.s, and then you run this instruction that I've highlighted, it will actually destroy any changes that you had made in myfma. So please be very, very careful. If you're using a make file, don't put that in the all. Basically, you're gonna have a bad time. All right, all right. Let's take a look at this code here. Okay, don't panic, everybody. There's going to be a lot of stuff here that's not relevant to what we're doing, stuff that we do not necessarily need, and a big part of being a programmer is identifying only the parts that you need. And basically here you can see this code. This thing is actually the stack frame. So basically here we have this top item must be the length. And the reason why I know that is it's an integer, and you can notice here W, meaning that it's 32. Integers are generally always 32 bits, except for in rare circumstances. The following must be pointer to A, pointer to B, and pointer to C. Remember that pointers in ARM, whether they're a floating point pointer or whatever, those are all stored as 64-bit integers, hence the X, okay? Yeah, so basically, remember, a memory address is always an integer. So a floating point pointer, actually its underlying data type is a long int, at least in this environment in ARMv8, okay? Here, this might seem a little less clear, but this is basically I equal to 0. Basically, you're storing 0 onto stack pointer 44. Remember that at the assembly level, you lose the notion of your variables. And then here, this might seem weird because your for loop was a pre-test loop, right? And it has you do an unconditional jump. GCC does this weird thing where, like, it has you jump arbitrarily into the loop test code. So basically, .l2, the stuff that I have highlighted right here, that stuff is the loop test. So basically, remember, SP44 is I. So this is loading I and then loading N. At least I'm inferring that's N. And it's going to compare I to N. And if I is less than N, jump to L3. So that means that L3 is our code, basically, that we can modify. Now, I'm going to rehash this sort of discussion here about what GCC is doing. A lot of these instructions seem really confusing. Like, for example, hey, wait, like I want A of I, like, can't I just have a load instruction where I just get a value, like from the stack or something like that? What's with these instructions? So basically, what you'll find, particularly with the -0 version of GCC, is that this whole math basically is attempting to perform some sort of pointer math where it is adding 4 times I to the base pointer, basically. So I'm just going to check here. So basically, SP16, that was the x1, the first pointer. So this is literally calculating the address of A plus 4 times I, literally every time in the for loop. Now, that might be a little problematic. That's like 5 instructions or 4 instructions that actually don't need to exist. So what I'm going to do here is, this isn't even related to SIMD or loop unrolling. I'm getting triggered here, and I gotta fix it basically. So we're just gonna set some temporary pointers to A, B, and C. All right. Technically speaking, you can actually directly modify x1, x2, and x3, actually, but meaning that you could basically just use those pointers directly. Just note that I'm actually going to do something different here, where I'm going to move stuff into certain registers here. So x1, so let me just do this. So we will have x19, x20, and x21. Hey, wait a minute. Hold up. What you're going to want to do is check your calling convention to actually see what the ARM calling convention is. Personally, I actually like to go to Wikipedia for this sort of thing. So if you Google the ARM calling convention and you literally scroll all the way down to ARM64, it'll tell you what all the registers do. And actually, I wanted caller saved registers, X9, basically. I'm not sure why I started at 19, so that's X9, 10, and 11. Otherwise, if I was going to use the registers that I pointed out earlier, we would have to save them somewhere in the stack. Let's not do that. So basically, what's going to happen now is X19 is the pointer to A, X10 is the pointer to B, and X11 is the pointer to C. Now, what I'm going to do here is I'm going to delete all this stuff, actually. If this is A, what I'm going to do here is basically dereference. I'm going to dereference this at 9. All right. So basically, let's delete this, delete this, delete this, and go over here. Okay, cool. So basically all of that just to get A, basically. And you can see I saved a lot of instructions. So actually, I'm just going to delete the whole thing, actually. And here's what we're going to do, people. We're going to delete this whole thing all the way down to here. Why did I do that? How did I know that I could delete all the way up to here? Well, this looks like I++, which is like literally the last thing you do, basically. So we're just going to leave that, basically. And then we're going to just have a sequence of instructions up here that basically will dereference the values we need. So basically, let me just put this in S0, actually. I'll put this in S2. And then this is 10, 11, and or 9, 10, and 11, basically. So I'm basically loading A, B, and C. And then what I'm going to do is we have to multiply. So that's fmul, by the way. Fmul, let's do S0, S0, S1. So we're going to use S0 as the aggregator. Then we're going to add S0, S0, S2. So basically multiply these two items, place that into S0, add these two items, which by the way, this was linked, right? So there's a multiplication right there. So this is A times B plus C, store that into S0. And then finally we have a store instruction. We're going to store S0 back into A. So that was the first thing. All right. Now, when you're doing this, by the way, like up here, I had set the pointers. Notice that you might have some alarms going off in your head, like, hey, we didn't increment the pointers. Actually, in ARMv8, they have this post-indexing format where when you're done with the pointer, you can actually march it forward with a certain addressing mode. Note that I'm putting this outside the brackets. So if you put it outside, that means perform the reference and then move the pointer forward by that many bytes, okay? So basically, the last time you use the pointer, you can just throw a comma whatever on it, and it would actually move the pointer by that many, okay? Keep in mind, though, when we move on to SIMD, some SIMD instructions, actually based on how they're like formatted in the binary, you'll have trouble getting away with this notation, and you might need a distinct like addition operation, basically, to make it work. All right, so let's just double check here before we move on. So we got A, we got B, we got C. At this point, these are the two times when we both have finished with that pointer, basically, and thus for both of those instructions, we march it forward by 4. We don't march A forward by 4 because technically we reference it later on, right? You have to get the value of A, do the math, and then store it back onto A. So basically, that's why you don't see the comma 4 there. This is the last point where the pointer is used. Then finally, that math, and then I++. We haven't unrolled anything or done any sort of stuff like that. So we can pretty much just leave this as is. Let's go ahead and quit out and recompile this thing. So I'm going to just compile this thing. You can compile this thing actually exactly as the instruction above. It's just that instead of doing myfma.c, you're going to do myfma.s. No errors. Cool. So let's go ahead and link this thing. Let me just try to find that instruction. So this one, nope. There it is. So here I am linking two uncompiled binaries. And what I'm going to do is I'm actually going to make this thing version 2. All right, cool. Let's go ahead and run this thing. Version 2.out. Wow, that is insanely fast. So actually, it looks like a majority of our optimization is actually due to me fiddling and reordering the instructions around and using the post index, but I'm certain we will still see an improvement. Okay, so please note that, people, that basically it looks like we were 0.19 seconds with GCC's version using -0. And then in version 2, just based on some advanced knowledge of assembly, we were able to get it down to 0.7, which is huge. All right, so let's go ahead and keep going here. So where do we go here? We can either do SIMD or loop unrolling. Let's do SIMD first. All right, so with SIMD, what we're going to do is we're going to let me copy myfma.s into myfma2.s. All right, I'm going to clear this. Let's go ahead and load myfma2.s. So on the assumption that the array is, the length of the array is a multiple of 4, you can use these SIMD operations that would grab up to 4 elements at once, perform the math, and then store the elements back. What do those operations look like? Actually, you honestly only need to modify a few lines. So basically, these are the vector operations, LD1. Here, I'm going to use vector 0.4s, and then I'm going to do v0.4s, and here, shouldn't be v0, it should be a different register. Just a sec. Okay. And then, like I said earlier, just based on my experience, I had issues with post-indexing and SIMD. So rather than perform post-indexing, what we're going to do is we're going to have some instructions at the end that actually increment the pointers as necessary. So I will just do that. Oop. Let's do this. Let's fix this stuff later for the pointer increment. So that would have to be 10 and 10. Okay, so going back up here, what did we do? So basically, the LD1 operation is a SIMD operation that comes with the A profile ARM64 or AArch64. Please do not confuse this with Neon. ARM has that thing where the major versions are not compatible, and Neon is with the previous version of ARM. It is not what I'm talking about today. We're talking about using the SIMD functions that are built into ARMv8 that are available on your Amazon EC2 instances, as well as your Apple M chips, basically. So this means basically to load, starting at the pointer x9, to sequentially load at that position 4 single precision floating points at once, and to stuff them in a vector register, a special register just for this purpose, with elements 1, 2, 3, and 4 in succession like that. And you perform the same thing for these operations, all right? Now what you do here is honestly nothing, basically. There's the same operations, basically, that are essentially responsible for the same operations that are essentially responsible for the floating point operations. You just call them again. It's almost like that you were supposed to be using SIM this whole time just for optimization. I honestly, for some environments, actually, I'm not sure if this happens with ARM, but the floating point registers are actually the vector registers, and when you're using scalars, you're just using them in a degraded state where you're only performing on one element at once, where it's hoping that you would use the SIMD operations as much as possible. All right. Okay. So anyways, one thing to note here, the brackets are only necessary for the load operations. When you're interacting with them in the math, you basically don't put the brackets. Note that you still have this funny .4s to indicate the number of elements in the vector. By the way, if you're coming and watching this video from a high level language, those are actually fixed. You have to look up the manual. You cannot just pick random numbers here, basically. It's designed to only work with specific combinations. I believe it's 2s, 4s, and then 1d as in double, or 2d for doubles. Like the vector registers are only big enough to basically hold 4 single precisions or 2 doubles, basically. Basically 128 bits, all right? Okay, let's fix this instruction now. So what would that be? That would be V0, 4s goes back onto x9. We're not post-indexing because I had issues with that before. So much of ARMv8, by the way, totally undocumented, and just based on my experience of like teaching this class over the past couple of years. All right, so let's see here. So basically, we have an array, and it is operating on 4 single precision floating points at once. And it's doing 4 workloads at once. So how many bytes do you increment the array by? So that's 4 elements times 4 bytes, 16. So you march the pointer forward by 16 bytes and not by 4, basically. All right. Another big deal here at the bottom, you're not doing I++, you're doing I plus equals to 4. All right. Okay, cool. So let's just review here. Funny load instructions to grab 4 things. Funny arithmetic that will actually independently perform those operations on a vector. And then funny store operation, as well as noting that the stride length had changed, both for our array increment math as well as I++ no longer being sufficient as I plus equals 4. All right, let's go ahead and run this thing. So let me find that instruction. Okay, so it's this one. I'm going to change this to be 2, and then I don't want to clobber the old one, so I'm just going to change this so that it basically compiles separately into 2. All right. Whoops. Operand 1 must be an integer register. Oops. Oh, whoops. Time out, people. Hold up. Anyway, sorry for the low production quality. I'm doing this only in one take. So, you know, with these, I changed them from LDR to LD1. Same thing goes for the store. It was saying it needed an integer here or some sort of general purpose register file because str was basically assuming you were working with scalars. So you change it to st1, and then that will then know to grab 4 elements, basically. Let's rerun that. Cool. All right. Now let's run the linker. So here I'm going to actually put 2 here, and then I'm going to save this into version 3. It's getting a little confusing with the numbering there, but hopefully you're able to follow along. No errors. All right, let's run this thing. Version 3.out. Cool. So the previous time was 0.07. This one is 0.04, 0.05 if you're going to round up there. So still, you could actually have a measurable improvement, although it seems that the biggest thing was that you're going to want to just simply even coding stuff or optimizing it in assembly by hand was a huge improvement. All right, let's go ahead and unroll this thing. So there was 2 parts, right? First, 3 parts: optimize it by hand, add SIMD instructions, and now we're going to unroll it. So what is unrolling? Unrolling is the idea that the microprocessor you're using actually has multiple data paths. The multiple data paths may contain multiple SIMD floating point units. So basically what happens is, instead of just having a for loop that does one thing, you're going to cut and paste the loop body twice inside of it and adjust the indices appropriately. And this further has the benefit of avoiding that many like control logic junctions, which might be the source of a control hazard, basically. So in order to loop unroll, the easiest thing you can do is literally to cut and paste. All right, I am illustrating the principle of code reuse. Yoink, and then paste. What happened there? So basically, I literally have 2 loop bodies where basically this thing is version 1, and then, or version 1 performing the workload on I, and then this one is version 2 performing the workload on I plus 4. Note that I still have the SIMD code in here. So basically, this would actually be I plus, because it's 4S, that's I plus 1, 2, 3. So that's 4 elements. And then this next loop would actually start at 4, 5, 6, 7, basically. All right. I suppose that you could save some computation by basically putting the correct indices here and then, incrementing it. But I guess the laziest thing you could do would be to literally cut and paste it. Note that inside the loop body, we actually are doing 8 times work here, basically, on a single step. So make sure to edit that, all right? Let's go ahead and step out here and try to compile that thing to just see. I didn't really change the name of my FMA2.s, but let's change it so it's my FMA3.0, all right? And let's go ahead and run this thing. Version 4 is using my FMA, my FMA3. Cool. What do you think is going to happen here, people? My goodness. That was slightly faster, I guess. So 0.036. Although I want to point out here that this is a really interesting requirement. Basically, this was highly academic, because if you're going to implement this, with this loop body, your array had to be, the length of your array had to be a multiple of 4. And that was a little strict. I mean, you could downgrade this so that it was basically 2S. I mean, you're probably going to have an even-sized array. But, I mean, 4 is kind of a weird number. And then on top of that, we unrolled it so that it did twice the work. That basically means that your array has to be, the length of your array has to be a multiple of 8. And that is, that might be a bit much, basically. All right, cool. And whenever you're doing this, please don't forget to check the array increment. A lot of people forget to update that accurately and then end up with longer times. All right. Okay, so key takeaways here. I guess doing it by hand actually is much better than what GCC produced, although I do want to warn you here, I use the -0 flag. I'm sure the GCC could do an okay job, but it probably wouldn't be as good as an assembly developer who knew what they were doing. All right? Anyways, that's it for the briefing today, people. Have a great day.